Video, I'm going to discuss how Euler's method works. So Euler's method is used to solve first order differential equations. Now the idea is that when you have a first order differential equation, you know the slope at every point in the function for which is the solution to that differential equation. So we know, for example, x prime, and the solution we're looking for is x of t. Okay, so the solution to a differential equation is a function. We know the slope of that function at every point, and we want to know what is the function. Euler's method starts with the Taylor series expansion, as I've shown up here. So the Taylor series expansion for a function, any function, we'll call it x, is the value of that function. You need to have a known point. So you need to know one point on x. And then you need to know the slope of that function, the second order slope, the third order slope, etc. X prime, x double prime, x triple prime, etc. Now, this is the Taylor series expansion. This is the definition for the expansion of x. What Euler does is it removes the higher order terms higher than first order. So the x double prime terms, the triple prime terms, etc. And it approximates the value of the next point based on the value of the previous point, x at a, plus the slope at the previous point times h. Now, if you recall, we have a line. So a straight line function this is a straight line, has a rise over a run. And m, the slope, is rise over a run. H here is identically the run. So if this is my starting point, okay, I'm going to show you on the curve next, but this is my x of a, then I can predict x at a plus h, okay, and h is this run, this is h. So my rise becomes, if I reorganize m equals rise over run, my rise becomes m, my slope, times my run, which is x prime at t times h. Okay? And if you look at the equation we have here, this guy is x of a plus, so the value at x at a plus h, if you look over here, this value right over here is given by x at a plus this extra amount here, right here, which comes from the slope at a, okay, x prime t times the run. Okay, so this is how we compute the next point. Now, if you look at this, this graph that I have here, move it down here for a second. What you notice here is if the actual function right here, this is my x of t. Okay, that's the actual solution, the non-numerical solution, let's say. The fact that we ignore these higher order terms here, that's the source of error in this method, because this method is a first order term because it ignores all but the first order slope. Okay, and when you're when you have the tangent to a curve and you project that out the way we do here, okay, so we have a point, we're basically projecting that point out, ignoring the curvature at that point, that's going to generate this error. Okay, all right, so now we understand some of the limitations. If the step size is small, then what you notice is you see the error terms, h squared, h cubed, etc. Then those terms become smaller and smaller, because when you cube or you square a small number, that number becomes even smaller. So choosing a small step size when using this technique is very important. Okay, so what's next? So let's do an example. Okay, I'm just going to put some numbers down, and we're going to use these numbers to do some computations. Okay, just to show you how this method actually works. Okay, so let's imagine that we have, let me draw a curve here. So what we know, this is the known. We know x prime at t as a function of t. And here, let's pick something that's really, really easy. Okay, I'm going to draw a straight line. Okay, and this guy, okay, this is dx by dt. So dx by dt equals, let's say, 2t. So it's a slope, right? So the slope here is 2. Maybe I'll just draw it as m equals 2, just to make this very, very clear. M equals 2. Okay, that's the slope of that line. So what do we expect? We expect, look, if x prime at t equals 2t, how would you solve this? Well, analytically, we would, basically this is dx, this is a first order differential equation by dt equals 2t. Okay, and that means we'll separate the variables, dx equals 2t dt, and now we can integrate both sides. And so this is x plus c equals 2t squared over 2 plus, we'll call this c1 and this c2, no problem. This guy becomes x equals t squared plus, okay, c2 minus c1, we'll call this c, okay? So x equals t squared plus c. And so this is the family of possible curves. Okay, now, this is the general solution. Okay. Euler can only give you the particular solution because it needs a starting point. It needs a point, needs you to know a point on the curve. You need to know x of a. You see right here? You need to know the very first point, one point on your curve. So let's make our example where c, so for us, we're going to choose the particular solution where c equals 0. Okay, so I'm going to draw the solution. So this is the x prime. Okay, the solution, the exact solution is going to be, this is x of t. Okay, my exact solution is going to be this. So it's t. Okay, we're going to get some points on this curve. Okay, so let's go like this. I was too early in my... Okay, that erased the whole line. Okay, let's get a couple of points on here just to make this very clear. Okay, I think that's as far as I'm going to be able to go here. Okay. All right, we're going to go t is 1, t is 2, t is 3, etc. Okay. Maybe what I'll do... Let's make this a little nicer. Let's clear this up a little bit. Here's what I'm going to do. I'll just take points in the middle here. Oops. Okay, and what we'll do is we'll grab these guys here. Okay, so if t is 1, then x of t should be 1. If t is 2, then x of t should be 4. If t is 3, then x of t should be 9. Okay? And now the question is, what does our algorithm tell us? Okay? How can we solve for x of t given that we know x prime of t? Okay. So let me take these ones out. Let me clear this up a little bit. And we'll just get rid of that. So we know what we're working on. Take this out too. Let's delete that. Okay. All right. So what does our algorithm give us? Well, we know x prime of t. So let's put in all of our x prime of t. Let me put this here. X prime of t equals 2t. So x prime at 1 is equal to 2. X prime at 2 is equal to 4. X prime at 3 is equal to 6. Okay, let's keep going. X prime at 4 is equal to 8. X prime at 5 is equal to 10. Okay, we can add more points here to make our okay. These are the real points. Okay, I can't go to 5 on my curve is a little too much. But anyway, okay, so these are the knowns. And now what we need to do, we know the actual values, right? So 4 squared would be 16, 5 squared would be 25, etc. Okay, so these are the actual values, 25, 16, 9, 4, and 1 for these. But what does our algorithm give us? So I'm going to change the color. Okay, so our algorithm says, let me write down the, so these are the knowns. Actually, go back here. And this is the Euler. Let's write the formula, and then we'll just follow it. So the formula is x at a plus x prime at a times h. Let me just move this up a little bit here. Okay. So it's x at a plus h equals x at a plus x prime at a. This is known from here. Okay, we know this one times h. Now in our example, I'm just gonna pick. So I'm gonna say pick, just to make the numbers easy. H equals 1. The step size is huge. Okay, so this is gonna show big errors from what the expected values are gonna be. Okay, so let's pick h equals 1. Okay. I think this color is a little too light for my liking. Let me change that. Let's go with blue for now. Okay, there we go. All right, so pick h equals 1, and we're gonna start Euler's method. So we need one point that we know. So we know x prime, and we also know one other thing. We know that x at 1 equals 1. This is the known point, because remember, Euler's method is going to give us a particular solution, so we need an initial value. All right, great. So let's do that. So we say x at 1 equals 1. Okay. x at 2 equals, well, we need x at 1 plus what is the slope x prime at 1? Well, that is 2. And what is h? That is 1. Okay? So what is x at 2? Well, x at 1 is 1 plus 2. We're given 3. Okay? The actual is x at 2 is actually 4. So we're off by 1 here. Okay, so you can see where we are on the curve. I can put it here. We basically drew the curve from, okay, so this is a straight line tangent to the point at 1. We projected it out. Our h is here. Okay, I'm going to zoom in a little bit. Our h is here, and this is the error. Maybe I should color it in red. This is the error. Okay. Oh, anyway, let's keep going. Okay, back to blue. Let's compute x at 3. X at 3 is x at 2, and you can start to see that the error is accumulating because this is going to be, well, x at 2 is going to be 3. Okay, plus, let me clear this one, plus x prime at 2 times h. Okay, so this becomes x prime at 2 is, okay, so we use x prime at 1. X prime at 2 is 4 times, now h was 1, so we're going to 7. And the expected value at 3 is 9. So you can see we basically took this point, okay, this blue point. We're using the slope here, this slope, okay, but we're taking that slope and we're putting it right here like that. I should really come in with better. Unfortunately, there's no ruler that can be, I mean, I could use a ruler maybe. But anyway, that's what we're doing. We're taking this point, the slope, the tangent. Maybe I'll use only a few colors to choose from. But anyway, we're basically taking the slope, okay, that's known, and we're basically projecting out, okay, and that's giving us the next point, okay, and you can start to see that the error is accumulating. So the actual here x at 3 is 9. So the error is 2. Okay? So anyway, we're going to keep going. So the same, now let's do x at 4. Okay, equals x at 3 plus x prime at 3 times the height. So what was x at 3? Well, that's taken from the last point, 7. X prime at 3, if we look, is 6. And h, we're just using a step size of 1. And what is 7 plus 6? Okay, that's 13. But the actual x at 4 is 16. Okay? So basically what happens is we have these sort of straight line fits, okay, to each of the tangents that we know those slopes, and we simply take the previous point, okay? We take the previous point that we calculated in the previous step, and we use it in the next step. We take the known slope times the step size, okay? That's, we know from the differential equation, and then we get the next point. And then, again, we use that point plus the slope times the step size, the slope that we know from the differential equation, and that gives us the next step. And basically this allows us to sort of pointwise, okay, if I get the blue again here, approximate, okay, with curves here, points that that come close to the actual value of the solution this x of t that we're looking for. Okay, and the smaller the step size, the less this error, and the more that the points that we plot line up with the actual function, with x of t. Okay, I hope you enjoyed this video and going through these steps, and I hope this makes clear how Euler's method works. See you next time in math class.